Today we're going to look at time-bounded dynamic memory allocation. And one of the allocation algorithms that we're going to look at is the two-level segregated fit. We're going to see why that is important and where it's used. All right, so why just not a memory allocation and free, the normal that comes with the operating system? Is because there are many applications that require very low latency on the system during memory allocation, and they need to be time bounded to a maximum. And one example is games. So everybody experienced this already when they're playing a game, and sometimes the game just hangs for half a second. That is usually the reason is usually because there are some memory operations that are happening on the background that needs to readjust the position of the memory and the allocation, and that causes the delay. On a game, that's no problem, but if you're talking about mission critical systems like high frequency trading, medical devices, CNC machines. You're cutting, a piece of aluminum, and that's very expensive. The machine cannot hang for half a second or even 300 milliseconds, 200 milliseconds, and then you're gonna lose your what you're doing, and that's very very costly. And those type of systems they require very precise delays on when the system is running and as I said, one of the main causes of those delays are memory allocation and memory fragmentation. So memory allocation delays, the first one reason is external memory fragmentation. That means when you have your piece of memory, if you imagine a really big vector, let's say you have four boxes where you have 30 bytes in each. So you have A, B, C, and D. They all have 30 bytes, and they're different variables. If you free box B and D, now you have a total of 60 bytes free in memory. But if your application tries to allocate 40 bytes, you don't have 40 bytes continuous memory that you can give it to your application. So you have to coalesce the memory, you have to um, consolidate the memory, you have to move block C next to A, so you have 60 bytes continuously, or at least 40 to give to your application. So this movement of memory takes time, and you have to pause. Basically, you have to pause the application to do that. That has also consequences on the processor. You're gonna invalidate the memory translation map that the application uses. You have to rebuild that, so that there's a lot of cache misses involved on this process. Another reason is internal memory fragmentation. That is when you allocate, let's say, 30 bytes and the application gives you 40. That are some reasons for doing that as well. Is one of its the alignment of memory. Um, there are requirements of memory to be aligned to what the CPU can load and how the CPU loads the memory inside of the cache. As I said, free blocks consolidation. The blocks needs to be moved, um, sometimes many times until you find a continuous enough piece of memory to give to your application. And you have other system calls that interact with the memory, which can give you micro and milliseconds delay. If you allocate memory which is outside of what the normal memory allocation expects, then you have a memory map, and those are a little bit different. These memory allocation algorithms need to be multi-threaded. So if one thread or one part of the system is doing a memory allocation and that process happens to have another delay because it's doing some other calls, let's say IO, then everybody has to wait. All right. So then the one of the solutions for this problem, there are many different algorithms. This is one of the latest. Is two-level segregated fit, and then for two-level, we're gonna look at why that is. But this algorithm has a fixed amount of time that it performs allocation. That's very low latency, and it's always fixed, and has very low level fragmentation. The memory is divided on the first level. That's why two levels. The first level, the blocks are in power of 2. And the second level, which is low internal fragmentation, is inside of the second level, every power of 2 block moves in increments of sizes. So every first level is a power of 2 gap, and every second level is just incremental. Uh, there are no remappings of address when you allocate or deallocate, and the coalescing of a memory is fixed. So a coalescing of a memory is when you have, let's say you have block A and B, and A is used and B is free, and they are sit next to each other. And now we want to free block A. So now we have two free blocks, one next to each other. So what you want to do is coalesce them in a single block, single big one. And that's a fixed amount of memory because you're always going to coalesce one block to the previous and to the next one every time you free memory. So it's always 3 blocks maximum. So this is fixed. And there are no heap expansion delays. The heap expansion is when your application starts, it has a certain amount of heap memory that it can allocate. And if you go above that, you have to re-expand the heap to larger size. And then the larger size, you have to see if there is enough larger size inside of your RAM. And then if you don't have, you have to move all your heap to this larger piece of heap, and then yeah, that's the copy thing that we talk about. So there's the delay. For two-level segregated fit, every time you need more memory, you just insert a new block, or you just remove a new block. So if you need more memory, just insert it, and then you start using, and then start cutting, and that's how it works. So this is a visual representation of what a two-level looks like for the memory allocation. So they have the first level, you have a 32-bit int, and this is just for a 4 gigabyte memory space. So you have your 32-bit, and every bit represents a level, which represents a power of 2 level. And inside of every level, then you have your, so let's say think of this horizontally, and vertically you have another integer, or mm, like a 405-bit. Let's say you have a word. So you have a 32-bit, which represents the second level. And every time the bit is 1 in the first level or on the second level, it means you have a free space on that position. So if you, let's say, you wanna the 89 byte size memory, so that is on position 6 on the first one, and then the position 6 from the 16 to 32, then then you know that this block is free. So the search for a free block is just 2 steps, always fixed. And inside of the block itself, you have the block of memory, which is the big square. So the big square is the block of memory, and every memory has a header, and this header has a pointer to the next block, a physical pointer to the previous block when you need to coalesce and all those things. So let's take a quick look at the code now. This is on my GitHub. This one particularly is very old. I'm working on an updated version. But basically, everything starts at the initial memory allocation. So you have how many power of 2 bytes you want to allocate. So everything is pre-allocated. It's not like malloc or free type of thing, which the memory, it's still not allocated. This holds the entire size, the entire block in memory already. And then it allocates all the bytes that you want to have available for anyone to request. The first block, so you said the everything that is allocated has a header. So that is the first block. You zero out everything. So you set the size of the block. You see where on the first level and second level this block is going to be. Again, that's dependent on the size of the block. You have the first level is power of 2 separations, and the second level is incremental separations. Set the block as free, and you insert your first block on that position. Then later, when you want to allocate, so that's the allocation. So when you want to allocate, you verify here some stuff. It used to have still initialized. You see where this allocation would a free block would be. So the idea is basically you look at the size that you want to allocate, and you always pick a higher size, and you have to look into where it would be. And the idea is mapping search. Yep, it's just a numerical calculation. You look at the higher bit inside of your requested bytes, and the second level is just a couple of bits. On this one particularly, I think it is 3 bits. So the second level is just composed of 3 bits, and so split, yeah. So that's how you get the first and second level. So you search where it is, and you get the block which is free on that position. This is the block, and the block will be larger than the block you're requesting. Was if the block is larger, of course you're going to remove it first, and then if the block is larger than so the difference is larger than the threshold. So let's say you requested 60 bytes and the block is 100, and that is over the threshold. Then you have to split the block because you don't want to give the full 100 bytes to the application that only needs 60. That's internal fragmentation. You want to minimize that. So you split that blocks to a remaining block, and the remaining block gets reinserted into the the control. And the pointer of the block, you have to remember every block has a header. So here you jump the pointer. So the first byte that you can write is after the header. That's why you jump on the block header size. And once you wanna free the memory, you jump backwards. So once you get the memory, you jump forward on the size of the block, and once you want to free the memory, you jump backwards the size of the block. That's the block, and then you try to merge the block with the previous block in physical memory. There is two distinctions. The blocks points forwards and backwards, but that doesn't mean they are sequentially in memory. The previous and the next block here in the free are the ones that are sequential in memory. There's a distinction to that. Then you merge previous, you merge next, you try to merge at least. That's the coalescing of memory. And you insert these coalesced blocks back to the controller. And the reason I'm looking into this is because I'm planning to build my own Linux distribution. Currently, there is available kernel, which is preemptive RT. That is what the market uses for uh, decreasing the jittering and the increasing preemptiveness of the kernel threads, so your application doesn't get hanged if something is happening within the kernel. So the threads on the kernel can be taken out of the CPU. But there is a gap on memory allocation. There's a gap on the CPU isolation and the use of P and E cores. The P and E cores are the performance cores, and E are the economy cores, like economic cores, or uh, which are basically smaller cores. They use less energy and energy efficient cores or something like that. So they use less energy. They have smaller cache. They have smaller bandwidth and lower number of processing units inside of them. That the ports, I think they have like 6 ports instead of when a P core is a performance core, they have 12. And the L1 is larger, the L1 cache is larger as well. So there's just kind of a performance processing. Um, Try to move all the OS into the e-cores, all the application, customer application on the performance cores, and do not allow kind of separate the operating system from touching the P cores, and have those be only scheduling customer process. Also use the Intel performance counter monitors, the cache pinning, and other libraries that will allow the process to have a very low latency and no jittering whatsoever. So that's kind of the reason looking into memory allocation and um, low latency memory operations. So let's see what comes out of it.